Today we're going to we're going to backtrack a little bit. We're going to go to writing proofs. Now we've already looked at how to write proofs in terms of triangles, but we're going to look at a couple different ways to do it now. Before we do that though, we got to get through this stuff, and we've looked at postulates before. We've looked at a bunch of different postulates, but here it's giving us an actual definition for what a postulate is. It says postulate is a statement that is accepted as true. Postulates describe fundamental relationships in geometry. So we've got all these different postulates, 2.1 through 2.7, that gives us these different relationships that we use in geometry. I'm not going to go through and read all of them to you, because you guys can do that on your own. But I want to show you how we're going to kind of use them. So for example, you're going to see problems where they give you examples of different properties, and you're going to have to be able to say whether a statement is always, sometimes, or never true. So for example, the first one says there is exactly one plane that contains points A, B, and C. Is that sometimes, always, or never true? Well, the answer they give us is it's sometimes true. If A, B, and C are collinear, they are contained in many planes. If they are non-collinear, they are contained in exactly one plane. The reason I know that is because of this right here. Postulate 2.4 tells me that. It says a plane contains at least 3 non-collinear points. So using that information, I can deduct that. I can also go up here, and it says through any 3 non-collinear points, there is exactly one plane. So again, in all of those, it's talking about non-collinear. So if they're telling you they're collinear, it's not always going to be true, but it will sometimes. Let's look at another one. B says points E and F are contained in exactly one line. Always true. And it says my first postulate gives me that answer. Right there. Through any 2 points, there is exactly one line. 2.1 gives that to me. And then the last one there, 2 lines intersect in 2 distinct points, M and N. Answer being never. The intersection of 2 lines is 1 point. And I can see that here. 2.6 tells me if 2 lines intersect, then the intersection is exactly 1 point. And that's kind of common sense. We've done that before. So let's move down here. And I'll do a couple of these, and then I'll have you try a couple of them as well. So again, it's saying determine whether each statement is always, sometimes, or never true. Number 1 says a line contains exactly 1 point. You're going to want to refer up here to these different postulates to tell me if that's true. Right off the bat, I can see 2.3 tells me a line contains at least 2 points. That postulate right there indicates to me that this statement is never true. Doesn't work like that. Number 2 kind of relates to the example that we just did. Non-collinear points R, S, and T are contained in exactly one plane. Again, if I go up here, 2.2 again leads me to that response. Through any 3 non-collinear points, there's exactly one plane. That's exactly what that says. That is always true. And then I'll do number 3 as well. It says any 2 lines, L and M, intersect. So, excuse me. We don't really have a postulate here that necessarily points me in the direction of that answer. But I do know, just think about the nature of lines. We know just from our work in this class and other classes that there are certain types of lines that don't intersect. Think about parallel lines. Oops, that doesn't look very parallel. If I put that on there, it is. Parallel lines, the definition of them is they never intersect. But there are other lines that are going to intersect. So that's one of the cases that I'm going to say, okay, that's sometimes true. Why don't you guys try 4, 5, and 6? Okay, now I apologize in advance for how long these notes are. And I want you guys to try 7 and 8 as well, because that's really what I was doing in the first part. They're telling me that these are true. They want you to actually point to that postulate. So which postulate tells you exactly one plane contains points F, B, and E? And which postulate tells you that line BE lies in plane Q? So take a look at those postulates again and see what you come up with. Okay, the next thing we've got, and I'm going to try to go through these a little quickly so that the video isn't too long, is they're actually defining a proof for us. Now there's a couple different kinds of proof, and we've seen these words, I believe, on a couple of the things that we've done, but we actually haven't followed through with them. So, again, a proof is a logical argument that uses deductive reasoning to reach a valid conclusion is called a proof. A flow proof uses statements written in boxes and arrows to show the logical progression of an argument. We're not really going to do too much of those. Another type of proof is a paragraph proof, where you write a paragraph to explain why a statement is true. Now, as an example, they gave us this. They're giving me a given, like I was given in my triangle proofs. And it says, in triangle ABC, BD is an angle bisector. Write a paragraph proof to show that those two triangles are equal. That those two angles are equal. They are very wordy in this, and they say, by definition, an angle bisector divides an angle into two congruent angles. Since BD is an angle bisector, ABC is divided into two congruent angles. Thus, this is equal to this. That is a very wordy little way of putting it. And again, kind of like with our triangle proofs, there's not necessarily one specific way to do these. As long as you are saying things that logically make sense, that are mathematically sound, you're good. So let's take a look at these down here. So for example, they give me, my given is that the angle A is congruent to angle D, and angle D is congruent to angle E. Write the paragraph proof to show that angle A is congruent to angle E. So, I'll show you what the book kind of wants us to do and gives us. So what they're saying, and I think we talked about this a little bit, these can get a little bit wordy and you're very detailed. So I'm going to say, since angle A is equal to angle D and angle D is congruent to angle E, the measure of angle A is congruent to the measure of angle D. Or I don't even want to say congruent there, because measures aren't really congruent. Measures are numbers, so they are equal. The measure of angle A is equal to the measure of angle D, and the measure of angle D is equal to the measure of angle E. Okay? The next part, we have talked about it a little bit. If I have got two things that are equal to the same thing, I can say that those two things are equal. So I'm going to say that was the transitive property. We talked about it very briefly. By the transitive property, the measure of angle A is equal to the measure of angle E. And then I'm going to kind of unravel it back to what our original form was, where they said this. So, angle A is congruent to angle E. and we can say by the definition of congruence. A lot of this stuff, again, do not worry too much about making it look all pretty like that. We're not even going to do too much with paragraph proofs. And then you'll notice we are where we wanted to end up. So why don't you try this one? Give that one a shot and see what you come up with, and we'll talk about that one a little bit more. Pause the video and do that. Okay. Let's take a look at the next set of notes. Again, I apologize for the length of this video. It might be a little bit longer than normal. Another type of proof that we're going to look at is algebraic proofs. So they give us a couple different definitions here. Algebraic proof is made up of a series of algebraic statements. A two-column proof is what two-column proof and formal proof are very, very similar, and it's kind of what we've been doing already with our triangle proofs. We have two columns, one being a set of statements, the other being our reasons for making those statements. Much like what was on the previous page, we have all of these properties of real numbers. But you know all of these properties. These are the reasons that you do math. This is why you know how to do different problems. The way that we are using these is to take some things that maybe are kind of second nature to us, like this, where we would solve for A, and kind of pinpointing a reason for why I am doing what I'm doing. So again, I'm not going to read all those proofs to you, or all of those properties to you, but we are going to refer back to them relatively often. So, my first step here, much like any other proof, is just what they've given me. Reason being, given. Okay, I'm good with that. And then I'm just going to start solving it how I normally would, but I need to name a reason for why I'm doing that, looking at these properties up here. So the first thing I'm going to do is I'm going to distribute these. So 10 minus 6a minus 4a minus 28 equals 92. The reason I know that is because of the distributive property. Okay, so that's not too bad, because that's something we use relatively regularly. The next one is where things get a little bit goofy. Because now, okay, I'm going to do everything I can on this side. I'm going to combine my like terms. When I do that, I'm going to get negative 18 minus 10a equals 92. My reason for doing that, and this is why I said it was a little goofy, is by the substitution property. Because the substitution property says if I have one thing equal to another thing, aka if I have A equal to B, I can substitute A with B. The reason this is substitution is because I know when I do this operation, it is going to be the same thing as this. So my little 10 minus 28 is negative 18. That's technically my B, I guess, whereas 10 minus 28 is my A, and negative 18 is my B, so I can throw that in there. So on places where, and the same thing with the negative 6A and negative 4A. So pretty much places where you would normally say, oh, I'm just simplifying this, that's the substitution property. And we're going to see that relatively often here. Okay, my next step that I'm usually going to do, and this might look a little bit differently than how you might normally write it, and that's okay, but I want to get rid of that 18 on the left side, so I'm going to add it to both sides. You might typically, you probably add it down here, and that's okay. You can still do that. But if you're given like a little diagram, like or a little chart like this, it's a little bit easier to just write it in this form. That hasn't changed. The reason I'm doing that is by the addition property. A lot of these are basically just like, well, what are you doing? What are you doing to get rid of that 18? Well, I'm adding. I'm using the addition. I'm doing the exact same thing that I did up here. I'm using the substitution property again. This is probably the only one that I think is a little strange and confusing. Because if I do negative 18 plus 18, I get 0. So I'm going to substitute that 0 in on this line. And same thing here. I know that 92 plus 18 is equal to 110. So I'm going to substitute it in. And then my last step, I'm going to say, okay, negative 10a divided by negative 10 equals 110 minus negative 10. And I know that's the case because of the division property. And that essentially leads me to the answer. This is all kind of still part of the same step of actually doing that division out and getting the a equals 11. So all the math you are doing is something that you already know how to do. You've done it a million times before. You just have to name why you are doing it, which I know some of you are going to hate and are going to fight me on. But that is what an algebraic proof is. It's actually being able to essentially describe your thinking. So let's take a look at the next two. Actually do the problem for you. You just have to follow along and say, okay, well, how did I get there? So I'm going to go through and I'm going to just kind of give you the answers on this one and let you kind of take that in. My first step I was given. Second step I used the distributive property. Next step is substitution. Subtraction property. Oops, spelling. And then I actually use the subtraction property again. I'll give you a hint on that one. My subtraction here happened with my n, and my subtraction here happened with my numbers, my constants. And then my final step I get there because of the division property. So take a minute to kind of glance that over and see if you understand how I'm getting each of those things. Think about the actual math that you'd be doing to get from here to here to here, and see if those properties make sense. Once you do that, try number 3. Oops. Try example 3. And pause the video there to work on that. Okay. Hopefully you got through that. The last thing that I want to go through with you is this one right here, example 4. It's a little bit uglier than the ones that we looked at previously, but it's the exact same thing. So it says that the distance d an object travels is given by d equals 20t plus 5. The time t is the object's the time t the object travels is given by this. T equals d minus 5 over 20. Write a 2-column proof to verify this conjecture. What that basically means is they want me to solve for t, which they did down here. So I just need to provide the reasons for how I got from place to place. So okay, they started with this. I know that because it's given. The next thing I did is shown right here. D minus 5 equals 20. That, again, I want you to refer back to your list of properties at the top. And this one's kind of strange. This one could really be the subtraction or addition property because it depends on what you say you're doing. I can say that I'm going to add a negative 5 to both sides to get this, or I can also just say that I am subtracting 5 from both sides, and that's fine. So I'm going to say that this is subtraction. Subtraction property. Okay, my next step, naturally in doing this, if I'm trying to get t by itself, I'm going to divide each side by 20. Again, I'm just kind of following my normal procedure for doing this. I'm just throwing a name on the end of it. And the last part, typically you want your variable first, especially with these. So I want to say, okay, t equals, and this is kind of a silly one. It seems a little repetitive, but the reason that I can make that flip, if you look back at your properties, is called the symmetric property. Okay? So I'm going to have you try some more on your own. There are 2 more? Yes, 3 more in there. I want you to try 5, 6, and 7.